Hello everyone, my name is Praveen and in this video I'll be presenting my work playing chunk transfer dash segment at low latency with QLive. This work proposes a bitrate and a playback speed adaptation based on the queuing theory modeling of the dash client. While looking at the overview of the dash client, we can see that it downloads the video segment using HTTP request. And in the case of low latency streaming, the client uses the fetch API so that it can pass the chunk of the partially downloaded video segments and starts playing it immediately. These chunks are stored in the playback buffer and can be played even if the entire segment is not fully downloaded. Therefore, the latency is no longer directly dependent on the segment duration. In a dash client, a controller is responsible for deciding the quality of the segment. It also decides the playback speed to reduce the latency in case if our instantaneous latency is beyond the acceptable limit. The important point to note here is that even though we can play the chunks without fully downloading the segment, the quality changes still happens at the segment boundary. The controller can make the decision based on several factors such as the estimated bandwidth, previous quality, instantaneous buffer occupancy, total buffer capacity, latency, and the current playback speed. It is worth noting that unlike traditional video on demand, we cannot rely on the throughput for quality adaptation in the low latency mode. This is because the throughput doesn't give us the correct estimate of the available bandwidth here. To understand in detail, let's assume a network with zero latency. In such a case, we can hypothetically start playing a segment as soon as its first chunk is available. So if the segment has a bitrate of 2000 kbps and the total segment duration is 4 seconds, we'll complete the total 8000 kb of the chunk download in 4 seconds, and therefore the throughput will never exceed 2000 kbps even if the bandwidth is higher. To resolve this issue, we propose a method to filter download window for the number of bytes and the total time taken to download those bytes. We consider only those download window for which the total bytes downloaded are more than or equal to the MTU, and it contains a move flag as well. Such filtering allows us to have a correct estimate of bandwidth because having the chunks greater than or equal to MTU makes sure that the network was utilized to its full capacity, and the move flag indicate that the bytes that we have received at the client doesn't belong to two different chunks. Here, we also put the bytes greater than or equal to the MTU, not just equal to MTU, because at the browser level, sometimes the timer precision is not very accurate to measure the end of the chunk. And therefore, we observe a window where number of bytes that we have received are more than MTU. If we see the previous state of art approach, the entire filtering is done based on the flags to filter out the gaps or the idle time between the chunk. This approach fails when the latency is very low, especially below 1 second. And the instantaneous bandwidth makes the client to choose the representation level with the lowest bitrate. The situation corresponds to 340 seconds in the current picture. And in this situation, there is not enough data to filter out the gaps on the basis of flags. This phenomenon was not detected in the previous approach because there the algorithm used to slow down the playback speed if the instantaneous latency is below the threshold. And therefore, the latency again builds up to be more than a second, and then we have enough data to filter out. This is not the case with our proposed bitrate adaptation, and we'll see it later on. If we see the accuracy of the proposed bandwidth estimation method, we can see that the estimated and the actual bandwidth are very close, and the average accuracy is around 94%. Now, coming back to the system model for bitrate and a playback speed adaptation, we model the dash client as an MD1K queue where the total capacity of the queue is K, assuming the chunk of the segments arrive in the queue are independent and the service rate is deterministic and is based on the playback speed of the video, and there is only one decoding instance. Here, the arrival rate lambda depends on the bandwidth BW, the duration of the segment D, and its bitrate R. The service rate of the queue, that is mu, depends on the playback speed S and the duration of the segment D. The queue utilization rho is the ratio of lambda and mu. Here, we term the empty part of the buffer or the queue as the buffer slack. For MD1K queue, the rho and the average buffer occupancy have a S-shaped relationship. And for the ideal case where rho is equal to 1, the average buffer occupancy is half of the total buffer capacity, which is also equal to the average slack. Our previous work have shown that by choosing a representation level with bitrate R, for which the slack is nearest to the instantaneous buffer occupancy, we can converge the buffer occupancy to half of the total buffer capacity. This approach no longer works because the client need to determine both the bitrate and the playback speed. Also, the approach is bit aggressive and chooses a representation level higher than the network capacity if the buffer occupancy is high, which is risky in the current case for the low latency streaming where the buffer is small. In our current approach, we first calculate the row by considering the instantaneous buffer occupancy as the expected buffer slack, as in the case of ideal case of the row is equal to 1. Next, we calculate the product of the bitrate and the playback speed based on the bandwidth and row. And in case when the latency is lower than the required limit, we set the playback speed to 1, which is the normal speed. And then we can calculate the average value of the bitrate based on this value of the bandwidth and row. We keep the note of this value of R for the calculation of bitrate and playback speed for the other scenario. In case when the latency is more than the required limit and the buffer occupancy is high, we select a representation level that is one level lower than the bitrate calculated in the previous scenario. And then we calculate the playback speed based on this bandwidth, row, and the bitrate thus selected. In the third scenario, the latency is greater than the required limit and the buffer occupancy is low. Here we choose the lowest representation with minimal bitrate R1, and accordingly we can calculate the playback speed. So this is how QLive makes the combined decision on the bitrate and playback speed. Another work from New York University in this conference also highlights the criticality of balancing between the bitrate and the playback speed. We have compared QLive with 3 state-of-the-art methods under 3 different latency configurations with a limit of 1 second, 2 seconds, and 3 seconds, and with an average segment duration of 1, 2, and 3 seconds. Here, we always keep the segment duration lower than or equal to the latency limit. For example, for 1 second latency limit, we evaluated with the video of segment size 1 second, whereas for the latency limit of 3 seconds, we evaluated all the methods for 1 second, 2 second, and 3 seconds duration. We have carried out the evaluation under 6 network profile for 10 minutes. Profile 1 and 2 are from the Dash Industrial Guideline Forum. Profile 3 and 4 are from a 3G network dataset. Profile 5 and 6 are from a 4G network dataset. Now let's look into the comparison result. In this slide, we are showing the stalls and the number of stalls for all the 4 methods under different network profile for different latency limits. Here, the bottom left corner for each box is the most favorable condition where both stalls and number of stalls are minimal. As you can see that QLive is consistently having the lowest stall and the lowest duration as well, whereas other methods have variable performance. Specifically, you can see that Stallion in many cases for the profile 3 and 4 and for different latency limits is having significant stalls. Similarly, L2A is not performing well for 3-second latency limit for profile 1 and 2. The main reason why the compared methods are not doing so well is because they are calculating the playback speed and bitrate speed independently. In a situation when latency is higher than the required limit and the buffer occupancy is low, these methods increase the playback speed and eventually cause more stalls and thus increase the latency further. Therefore, this cycle of increasing the playback speed causing more stall and ultimately leading to a much higher latency continues for a while. In the next comparison, we are showing the average bitrate of the played segment with the changes in representation. Here, the top left corner of each box is the most favorable one where we have the maximum bitrate with minimal changes in quality. Here also we can see that QLive is having the maximum bitrate, but the changes in representation are also seems to be high, especially for profile P1 and P2. From the previous results, we know that QLive is not attaining this higher bitrate at the cost of the stalls. Also, the number of changes seems to be a bit higher, but they are still under 1/3 of the maximum possible value in the quality based on the segment duration and the duration of the experiment cycle. Looking at the average latency, we can see that QLive is always in the close proximity of the latency limits. even for the challenging scenarios such as profile P4, where the bandwidth is significantly lower. Other methods have higher latency, sometimes even for the profile like P1 and P2. This happens when algorithm chooses to increase the playback speed to reduce the latency at lower buffer occupancy and causing more stalls and ultimately higher latency. A similar trend can be seen for the maximum instantaneous latency, where also QLive is outperforming other methods by having the minimum value. Looking at the average speed, we can see that QLive is closer to the normal speed of 1x compared to the other methods, even for the fluctuating bandwidth profiles P3 to P6 for different latency limits. In the next result, we have compared the percentage of the total time for which a method chooses to play at the normal playback speed. This is to check if any methods have manipulated the playback speed too often to reduce the latency. Here we can see that QLive chooses to play at the normal speed for a much longer duration than the other methods, even though it has the minimal latency as shown in the previous slide. One interesting thing about QLive is that for 3-second latency limit, where we have 3-second segment, it plays at a normal speed for a lesser duration compared to the 1-second latency limit, where we have 1-second segment. This is because QLive changes the playback speed at the segment boundaries only. In contrast, other methods choose to change the playback speed whenever their latency threshold criteria are met. In the paper, we have even presented additional results on quality of experience and the effect of segment duration on the latency. Based on all these results, we can conclude that QLive performs much better because it establishes a relationship between all the factors such as bitrate, bandwidth, buffer occupancy, buffer capacity, latency, and the playback speed. Since the bitrate and the playback speed are calculated in conjunction, QLive can control the latency without any excessive modification in the playback speed. Overall, our bandwidth estimator is more robust and QLive plays the video at an average speed of 1.01 to 1.26 times the normal speed while having up to 97% longer duration at the normal speed without any sacrifice of the average bitrate or causing any additional stalls. Thank you.